Hello, everyone. This lesson today is about electrostatic fields. Okay, you're going to need your reference table as I'm going to show you a couple of things that you need to know inside the table. Um, then just simply follow along the presentation. And if you need to, you can repeat any part of it that you might have to go back to check on. Also, there's not much to the presentation. There's not that many slides, but then at the end, there's several examples. Follow along the examples so that it'll make it easier to do the homework problems after the video is completed. Also, today we're only going to be dealing with the magnitude. We are not going to deal with the direction of the field. We will deal with that tomorrow. Okay, so let's take a look at the reference table. Now, on the reference table, again, one of the important parts of this is right here, E. Again, this is the charge that is on the proton. It is also the charge that is on the electron. It's just negative. Now, I've said that several times. That's very important to understand because it'll never be stated in a problem. Also, if we look down here at the prefixes, you may need these values to make a conversion. The reason is because we always deal in coulombs, but coulomb is a lot of charge. So therefore, you may have to convert something like microcoulombs or millicoulombs and get it into coulombs by simply replacing the prefix. Okay, now the formulas. Inside your reference table, in the electricity section, okay, we have the formula that we've used and the new one for today. This is called Coulomb's law. This and Hooke's law and Newton's law, universal law of gravity, are the only ones that really have names that we need to know right now. There's another one coming up. This is the formula that we're going to use today. This is the electrostatic field. And over here, it's measured in newtons per coulomb. Okay, and if you go down the side, we can find all of these. Okay, the electrostatic field, that's here. The force is newtons. And of course, the charge, this is in coulombs. So just redirect this. This is the electrostatic field in newtons per coulomb. Force is in newtons, and charge is in coulombs, as the force is always measured in newtons, everything that we do. Okay, so now we're going to take a look at the slide presentation. Okay, so here we have electric fields, okay, unit 12F. That's not that important, the numbers. And what we want to do is go to the next one, and it says, is the electrostatic field real? Well, in fact, it is. The field applies a force on a net charge and can cause it to move. So therefore, it can do work. So it is real. The reason I say this is because the field is a rather abstract thing. You can't see it. The only way you can notice it is you can detect it with an excess charge. The symbol for field is a capital E, and it's measured in newtons per coulomb, and it is a vector, although we're not going to get to the vector part until tomorrow. All right. Now, what about the field? Well, the more charge that's creating the field, the stronger it is. Remember that magnitudes are just amounts. They're always positive. And here you can see the equation in its useful forms. The first is if you know the field at a certain point and you place a charge at that point, you can then determine the force that's acting on the charge by rearranging and placing the force equals the field times the charge. Now, that's why this is so useful, because rather than deal with Coulomb's law, charge to charge interaction, the field allows us to set up an environment all around the charge. And then if we want to place a charge at a certain position, we can easily find the field by just we can easily find the force by just multiplying it times the charge. Now, the equation for field is what I showed you. It's here. E equals the force divided by charge. Now, the units are very important because sometimes that can get you out of trouble when you're doing a problem. The electric field is newtons per coulomb. The force is newtons, and charge must always be in coulombs. Okay, so now what we're going to do is we're going to start doing some examples. This is example 1, okay? And example 1, you see a force having a magnitude of 15 newtons. So I'm going to write that down on a sheet of paper that you can't see right now. But this way here, I'll have the givens and everything for the problem. And it's detected on a proton, okay? So it's detected on a proton, 10 to the negative 19 coulombs. What is the magnitude of the electrostatic field at this point? Well, here's what we do. Let's go back to the Ziggy. And you can see that I wrote down the important points here, okay? And so we're going to use the formula. E equals Fe over Q, okay? And this is simply 15 newtons divided by 1.60 times 10 to the negative 19 coulombs. That is the charge on a proton. Now, this is rather unrealistic, but it's an example of the using the formula. That's all it is. Okay, so as I key that in, I end up with a huge field, 9.4 times 10 to the 19 newtons per coulomb. Okay, not very realistic, but you could see how easy it is to work around this formula. That's the idea. Okay, now let me go back to the slides and we'll take a look at the next problem. The next problem, example 2, okay, example 2. In this problem, a force having a magnitude of 2.5 times 10 to the negative 6 newtons is detected acting on a small sphere having a charge of 1.5 coulombs. What is the magnitude of the electrostatic field at this position? So what I'm doing right now, because I can't show you both screens, is I'm writing down the givens on a sheet of paper, and then we're going to solve for it. 5 coulombs. Okay, so let me go back to Ziggy. Okay. All right. Okay, so here I have the givens. And again, the formula is quite simple. E equals Fe divided by Q. Okay, so this is simply 2.5 times 10 to the negative 6 newtons divided by 1.5 coulombs. So the field at this point, and you should try it yourself, 2.5 e negative 6 divided by 1.5, and I end up with 1.7 times 10 to the negative 6 newtons per coulomb. So you could see that this is a fairly simple calculation. Okay, let me go back. I've got a couple more examples here that are significant. So you'll find these little things that you need to do. An electrostatic field having a magnitude of 250 newtons per coulomb. So now we're given the field, 250 newtons per coulomb, was detected at a point in space. If an electron were placed at this point, what would be the magnitude of the force acting on the electron? Okay, so again, there's something important here, and that's knowing the charge on an electron. I'm doing this exactly the way any problem that you're going to get would do it. Okay, so let me go back to Ziggy. Okay, so now here we have the problem. Okay, so now we have E equals Fe over Q, multiplying both sides by Q. Fe equals Q times E. Okay, so remember now, this force and the field, we're only dealing with the magnitude, okay? So that's what I'm going to do. I'm just going to put the magnitude here. We will decide on the direction tomorrow in different situations, different charge configurations. 250 newtons per coulomb. Notice that the coulombs are going to cancel, all right? And then we just multiply. And you end up with 4.0 times 10 to the negative 17 newtons. So an extremely small amount of force acting. Okay. Now, let's go back. We're going to take a look at another one. Okay, this one here. Notice now that there's a force of 2.5 newtons, okay, 2.5 newtons, acting on a 1.5 millicoulomb charge. What is the magnitude of the electrostatic field? All right, so I'm going to put down the givens again for you. So we have the force, electric force, 2.5 newtons, and we have a charge of 1.5 millicoulombs. And this is example 4. So let me just switch back to Ziggy. And you can see here, we got a problem. Millicoulombs, we have to get that in coulombs. So now on the front of your reference table, you'll notice that milli is 10 to the negative 3. This is it. So all you have to do is replace the prefix with the value. So this is equal to 1.5 times 10 to the negative 3 coulombs. These are about the only tricks you can find in this formula. You have to be aware that it must be coulombs. So now the formula, E equals Fe over Q. So we've got 2.5 newtons divided by 1.5 times 10 to the negative 3 coulombs. So the field at this point is 2.5 divided by the 1.5 to the negative 3. And you end up with two significant figures, 1,700 newtons per coulomb. Okay, now that's working around this formula, some examples. All right, now let's go back to the slides, just a couple more things. All right, as you can see here, whoops, sorry. Notice in the examples, the directions of the vectors, force and electrostatic, were not discussed. How do we determine the direction of these vectors? Well, we're going to do that again. We're going to do that tomorrow. There are several fields that you must know, but if you remember the few rules, you can reproduce them. So next we're going to be looking at the field direction, but that's tomorrow. So now I'm going to post this video, and then I'm going to post the homework next to it. Okay, there'll be 2 separate assignments. One of them you have already in your packet, but I'm going to put it up there just in case you don't have it. And another one is 3 new problems. Okay, well, until tomorrow, just stay well, and see you then. Bye-bye.